momentum again. So we've got conservation of momentum equals, well, I mean, we could say P is equal to P primed, or if you like putting totals in the subscripts, it's P total equals P total primed. Before and after momentum basically is going to be conserved. So let's put that into words. Total momentum before and after an interaction will be the same. Same for a system. And just to be clear that we all agree on what a system is. A system is a cluster of bodies that are somehow interacting with one another, but it includes, among other things, explosions and collisions. Okay? The reason I mention these guys in particular is because they're not attached to each other with ropes or something like that, which is something that we sort of like spend a lot of time with. So these are like separate bodies that are interacting with one another. Anyway, or becoming separate bodies after previously starting off as one body. So we want to split momentum up into X and Y components. And instead of just thinking about the total momentum before and after, we'd like to think about, we were able to do this kind of, not really, but with projectiles, we split things up into X thinking and Y thinking. So P total in the X direction would be equal to P total in the X direction after. And so we'd have an equation 1, MA VA, or at least the X component of VA, plus MB VBX equals MA VAX prime plus MB VBX prime. You start to see where we really wanted to have that prime notation, because AX initial and AX final, it's just like 3 letters. It's too much to take in the subscripts. So this is for a 2-body system. And we might have another equation. I mean, not surprisingly, PY total equals PY total prime. It takes on the same format. No surprises here. Okay, so it's a system of 2 equations. Now, the nice thing about these 2 equations is that we said before that momentum is always going to be conserved. And I'll even add on to that. I'll say that momentum is always conserved in the X direction, and momentum is always conserved in the Y direction. The nice thing about that is that both of these equations, if you take a quick look, are linear. The thing that's unfortunate, and we'll get to it as things come along, you can imagine that if they were talking about VBX and VAX, look at this. I've got a car crash at the bottom of the page. Can you imagine that embedded in that VAX and that VBX is probably a cosine theta or a sine theta or something like that? So while on the surface it looks like, oh, sweet, this is just like a nice system of 2 linear equations, they're not the same VAs. One's VAX and one's VAY. And hidden under the surface of that VAX and VAY is a trigonometry operator, okay? So it's better than a giant ridiculous quadratic or 3rd order equation or something like that, but it's not, your grade 9 math problem, basically. Yep.
For equation 1, you have VB and then VBX prime. It should be MB and then VBX.
Oh, yeah. You have 2 B's.
Do I have 2 B's?
You have the last one.
Yeah, the last.
Where?
The last. In equation 1, in the last.
Here?
Yeah.
I got VB and VBX primed.
Yeah, it's supposed to be MB.
Oh, you're right, it is M. Oh my gosh. I couldn't even see it. Forest for the trees. Thank you. I could not see the forest for the trees. Thank you. All right. That might have messed up somebody or nobody. I don't know, but at least it's right now. All right, so then there's an equation 3. And this equation 3 really is only going to be useful for us for perfectly elastic, because we've talked about the systems of equations involving partially elastic, perfectly inelastic, but I'm just going to state the perfectly elastic equation this time. So only perfectly elastic equations have the expression E total is equal to E total primed, but we will expand it out. But one nice thing about the energy equation, notice that I don't have to have x and y components, because energy doesn't care what direction you're going in. And again, I always like to put my primes in brackets so nobody thinks it, not that anybody would think it's to the power of 12, right? I'm going to throw in here, I know that this expression is for when it's elastic, but I'm going to say, hey, just so we don't have to keep on rewriting things, plus E lost if applicable. And if we're all doing our homework, then we know that there's going to be situations where we're losing energy, okay? So I'm going to tack that on there rather than writing out an extra fourth equation. Okay. All right, so to my car crash. And I'm going to slide these equations up. But I've got this car crash, and a few years ago, actually, I had a student in the class who had a parent that was an investigator of car scenes. Now, they actually worked for an insurance company. And so what I'm going to go through right now is the physics of it. And we had nice dialogue about how most of what we're doing right now has been put into, well, at the time, more spreadsheets and things like that. And now I assume more into apps and calculators to make this process faster, like to automate the process. But what we're looking at is the physics of what's going on. We're also, I mean, in theory, some of you could end up being computer coders, and maybe you're going to write the software that would expedite that insurance investigation or that police investigation. Okay, so let's talk about like the nuts and bolts of what's going on in this car, or in this car crash scenario. So the before in this case is the car A and car B driving towards each other. So we're going to put some values on here. Momentum A is equal to, let's just give it a value, 320. I'll put a line over top of the 0 to say it's 3 significant figures, kilogram meters per second. And we can just see that that's going to the east, but we can throw in a reference frame. This is an overhead view. We can make north be positive and east be positive, south negative and west negative. And in some ways, I regret that I have this illustration here with the car. So I'm going to do a little bit of white out here, just so I can see my vectors a little bit better. But I've got this momentum B, and I'd like to say that as this car drives along, they end up hitting each other, they get stuck together, and afterwards they end up having a P total that goes off in this direction. This P total is going to end up having a P total, a P total in the X direction. Oh, I should make that a primed. And it would have a P total in the Y direction, primed, and it's going to go off at an angle, theta. You don't really have to do this, but I'm going to call it theta primed, because it's the angle that they go off afterwards, as one body. Now, I don't actually know off the top of my head what PB was, but I'd like to claim that I was able to do a little bit of backwards calculations and figure out that PBX had a value of 200 kilogram meters per second west. I will put a line over that one there to give it 3 sig figs. I guess we can make this one east. And PB also had a momentum in the north direction. Call it PBY. So we've got a PBX, we've got a PBY of 150 kilogram meters per second to the north. And people say, well, where would you come up with that information? Well, I'd have to know what the initial theta was. And what I would probably have is somebody with a speed radar gun pointed at car B, right? And I would have some sort of a tracking mechanism, maybe a intersection camera, being able to figure out what that theta value is, and then I could use trigonometry to figure out the x component and the y component. Okay, so this is stuff that we could do. That's within the realm of feasibility. And if I wanted to go back and do those calculations to sort of recover what PB was equal to, we could say, okay, well, PB is equal to PBX squared plus PBY squared, all rooted. I'm not even going to do that calculation right now. I could also find theta, and I could use SOHCAHTOA. I think I would use tan theta is equal to opposite over adjacent PBY over PBX. So I'm just going to put a bubble around that, and you can make a note to yourself. We could figure that out, okay? Or we could just say we started with that information, with maybe some intersection camera footage. So we go up here, and we say, okay, momentum is conserved such that based on what we set up above, we're going to say that PAX plus PBX equals P total x primed. We're going to say equation 2 would be PAY plus PBY equals P total y primed. Recall, in this system, they stick together. So that would make this a perfectly inelastic system. In this case, P total x primed, well, let's look. Where am I getting my P total x's from? It's just going to be the sum of the horizontal bits, right? So I can just add them up. 320 kilogram meters per second. That's a positive value because it's to the east. We declared east to be positive. Plus negative 200 kilogram meters per second. That's nice head math, 120 kilogram meters per second. PTY primed. Isn't that just going to be the y component of car A, or car B rather? So we already got that, 150 kilogram meters per second. And then when we go to find P total, P total primed rather, P total prime is going to be P total x prime squared plus P total y prime. Oops, I put my primed in the wrong spot. Squared, all square rooted. A little help on the calculators maybe from you guys. 120 kilogram meters per second squared plus 150 kilogram meters per second squared, all rooted. What's the total momentum of this thing? This is when I don't have pre-calculated. So we're flying by the seat of our pants. What do you guys get? Yeah. 192.09. Yeah, okay. Kilogram meters per second. Now the other thing that we're missing is the angle, right? So it looks like theoretically this thing should go off at an angle of theta equals tan inverse of, let's take a look here. If this is the angle, the opposite would be PTY primed and the adjacent would be PTX primed. So we could calculate what angle this thing is going to go off at an angle, or what angle this thing is going to careen off at. So PTY primed divided by PTX primed. Maybe you guys can help me out. What's tan inverse of 150 divided by 120? I feel like I see three people that have got it. They're looking down because they don't want to answer. Anybody got it? Yeah? Nice. All right. So if I was going to say what angle this thing goes off at, or what the momentum is, it looks like, sorry, I'll leave it there just for a second. I'll bring it back again, don't worry. It looks like we're claiming that the final momentum of this thing is going to be 192 kilogram meters per second, and the angle is going to be east 51.3 degrees north. And that seems in line with the values that we're dealing with here in terms of the numbers. Look, this 320 and the 200 are kind of going to do battle with each other. It's going to drive it upwards. We have the 150 that's more or less going to be the same as the difference between these two. It's going to go, I would have eyeballed it going off at about 45 degrees, and we got it to be about 51 degrees. That seems pretty reasonable. Now, this is with all the information kind of just given to us, right? And so maybe traffic cameras can make all these observations, the before observations. Maybe one traffic camera is really confident about this one, but this one's going off at a weird angle. I mean, who drives through an intersection like that? And we got to figure out if the speed really was what it should be in terms of being within the speed limit. And we got to look at what the skid marks look like in terms of the angle. Can you imagine that the skid mark theta value could tell us something about how fast this car was going? Because of course we could take the mass of this whole system and take this momentum divided by the mass of the system and figure out what the velocity of these cars must have been. And we could do some speed investigations. And so that's what I want to do next. I want to take this basic idea, or kind of like spoon-fed out the thing, and I'd like to figure out if somebody was speeding in a car accident. A little insurance investigation.